Alright class, today we're going to describe the form of the titration curves for titrations of strong acid by strong base, also weak acid by strong base, and vice versa, strong acid and weak base. We'll calculate the pH at any point including the equivalence point and in acid-base titrations. This pairs well with the pre-lab. The pre-lab and the lab are all based around titrations, so this will be very helpful for that aspect. As we've seen in the third play posit, titration is when we have a known concentration of base and we slowly add it to a solution of acid, or vice versa, acid adding to base. We usually don't know the concentration of the second one, so we're taking something we do know, adding it something we don't know in order to find what we don't know. The reason this works is based around the dilution equation. Molarity of acid times the volume of acid equals the moles of base times the volume of base. What this really means when your volumes cancel is that moles of acid equal moles of base at the equivalence point. We also have what's called the endpoint, which is similar to the equivalence point. Equivalence point is when we have moles of acid equaling moles of base. The endpoint is where the indicator changes color if we're using an indicator. Often they are very close to each other, but they're not always the same, so I want to point that out. Something we'll see later. It's a good idea if you're trying to choose an indicator that the indicator has a pKa that is plus or minus 1, your target for your equivalence point. Okay. So first things first, a lot of things that AP will ask you to do is identify the parts of a titration curve, what they mean. It's usually good multiple choice questions. They even show up on the FRQs. So we have our equivalence point. If you look at the vertical portion of the graph, which is basically right here, and you go halfway up, that is our equivalence point. Alright, the pH at the equivalence point, like we said, this is where the moles of acid equal moles of base. So by knowing how much volume of base we've added in this version, in this first version of the graph, our molarity of our base times the volume of our base gives us the molarity of our acid, based on however many milliliters of acid we start with. And then therefore we can find out how many moles of A we have. This is between a strong acid and a strong base. If it's a strong acid, we know strong acids dissociate completely. We're going to have more H plus in solution. So typically you'll see low pHs when you have strong acids. Same with strong bases. We know that they dissociate completely, so you'll see pHs in the high range up here. The opposite is true if we're adding acid to base. We'll start with a strong base that's up here, and then we'll end with a strong acid. We know it's down here. If we are dealing with something like a weak acid, so I want to look at this one here. Weak acid, we know it's a weak acid because the pH is much higher than 1. You can see the difference between a strong acid and a weak acid. That is because our weak acids don't dissociate as much, so we only have a little bit of H plus contributing to our pH. This also caused a shift in our equivalence point, so we can raise in our equivalence point here, probably somewhere in the 8.5 region. If we're looking at this graph, we take just the vertical part and go halfway up. There's another important part, and first I want to identify what we're titrating with. We're titrating with a strong base because this is way up here. So this one's a weak acid and a strong base. Whenever that happens, you see there's this big region here, right here. It's this big region where the pH doesn't change that much. We refer to this as the buffer region. So this one This is where that comes in to play, is when we're looking at buffers, where things are resistant to change. Now, this is also a very important region. Based on the Henderson-Hasselbalch equation, we know that the H plus is equal to the Ka times the concentration of weak acid over weak base. Now, the other form of that you probably see on your formula sheet is pH equals pKa. pH equals pKa plus the log of A minus over HA. Well, when we are at the half equivalence point, half equivalence point would be halfway to our equivalence point. We know that pH is going to equal pKa because the ratio of HA to A minus is going to be 1, and log of 1 is 0. Therefore, the pH equals the pKa at that location. So if we estimated our volume here, let's see, our volume here is 25 milliliters at the equivalence point. Half of 25 would be 12.5, and right here, 12.5 is our half. So we could find our pH right there. Our pH is at 5. We could say our pKa is equal to 5 here. Okay, that's just based off of looking at the graph. That's a very easy and common question you'll see on the test, and they ask you about that. So half of the equivalence point volume is 12.5. Go to the pH. Okay. Here's another one. Again, weak acid, strong base. Weak acid, strong base, and then weak base. So a weak base and a strong acid. Here we see strong acid. A weak base, we're a little bit lower. If we were a strong base, we would be more up here. Okay. All right. One of the ones you won't see very often are I don't know if I have one on here. Weak base and weak acid. You won't really see that too much because it just causes too many problems. You've got two rice tables basically going in opposite directions. Not everything's dissociating. It's really complicated. Here are good graphs. You see there's two humps here. You've got chunk here, and then you've got another equivalence point here. These are for diprotic acids. So for diprotic, that means two H's. You could even have a triprotic acid. Titrations of a triprotic acid, you would see 3 humps, right? 1, 2, 3 for triprotic. Each of those equivalence points is based off of how many H's we have. Oh yeah, here's one. 1, 2, 3. Crazy. Okay. So let's do some examples. All right, time to do an example problem. This is from exercise 5 in your NAMESY packet. First thing off the bat I see before I even read this is I'm dealing with strong acid, strong base, meaning everything completely dissociates. So this is really nice to you. It says for the titration of 50 milliliters of 0.2 molar nitric acid and 0.1 molar NaOH, calculate the pH of the solution at the following selected points of your titration. Okay, well, first one's easy. We know that the pH is negative log of our concentration. We know our H plus is 0.2 molar. So if we do that, we get negative log of 0.2, and I get 0.699 as my pH. All right, 3 sig figs, 3 decimals. All right, so from here on out, is where it gets a little more challenging, but it's not too bad. We know because I'm dealing with strong acid and strong base, I'm looking at H plus OH minus. So this one's going to be easy for us because we're forming water each time. All right. Now I'm going to deal in millimoles for this. So 0.2 times 50 is going to give me 10 millimoles is my initial concentration of H plus, and I'm going to assume that, oh, it tells me 10 milliliters of NaOH, so 10 times 0.1 is going to be 1 millimole. All right. So the nice thing about this problem is as we go, it's pretty much a serial dilution. What that means is that our volume is going to go up, and then we have to look at the difference in our H plus concentration each time. So it's a limiting reactant problem. If we look here, H plus is in excess, therefore all of our OH is going to limit us, and if all of our OH is going to go away, -1, -1, we end up getting 9 millimoles of H plus, and then we divide by our total volume. Our total volume here is going to be 50 milliliters plus 10 milliliters, 60 milliliters. If I divide, my milli part cancels, and I get 9 over 60. 9 divided by 60 gives me 0.15 molar H plus. All right, now I have to do the pH of that. So negative log, and my pH is going to be equal to 0.824. 0.824. All right, so my pH goes up a little bit, but not by much. All right, so as we go through this, we're looking at the total each time. All right, so the nice thing is that basically starting from scratch, when we're looking at the total, our OH minus concentration doesn't change. It's still 10 millimole, and each time we just have to figure out what the new OH minus is. So 20 milliliters times 0.2, this time that puts us at 2 millimole. So 20 times 0.2. Oh, sorry, 20 times 0.1. Got to make sure I check my right concentrations, right? 20 times 0.1 is 2. All right, and same deal. I'm still in excess here. -2, -2. I'm going to get 8 millimole of H plus over, this time my total volume is 70 milliliters. Milli cancels. 8 divided by 70. I get 0.114 molar, and then a negative log of that. All right, 0.942. Pretty easy so far. Hopefully you catch the drift. I'm going to have you do the next one on your own. Same deal. If you've got 50 milliliters total of NaOH this time, what is my pH going to be? All right, should have gotten a pH of 1.30. All right, now here's where it gets tricky because we're finally at our equivalence point here. All right, so H plus OH minus H2O. Again, we started with 10 millimole, and 100 milliliters times 0.1 gives us 10 millimole. Therefore, we're equal, right? If it's a strong acid, strong base, what did we say? Our pH is 7 at the equivalence point for strong acid and strong base. Didn't even have to do math there. All right, last one. H plus, OH minus. And then I got my H2O. Still got my 10 millimole. And this time, 200 times 0.1 means I'm at 20 millimole, which means I have 10 millimole in excess. My H plus is now my limiting reactant, right? Excess OH minus, which really means that if I do 10 millimoles of OH minus over my total volume, which is 250 milliliters. This gives me concentration of 0.04. All right, 0.04 molar. I do my negative log of that. All right, and then I get 1.398. I'm going to say I'll just say 1.40. 1.40. Am I finished? No, this is pOH. So really that means my pH is going to be 12.60. 12.60. Boom. What a lovely problem. Serial dilution, several steps. You just have to keep track of your total volume each time because it changes, and that changes your molarity. All right, let's do another one. Exercise 6. This one's looking at hydrogen cyanide gas. I like this problem a lot because it incorporates both the buffers and some of the weak acid Equilibria stuff that we've done, and even some of the salt stuff we've done. It's a good culminating problem where it has all the different parts here. Okay, so it says we have a very weak acid, and we have our sample titrated with a strong base. Okay, so we've got weak acid, strong base. All right. So this one, since you've done some buffer stuff already, this is a Henderson-Hasselbalch equation problem. You've got 8 milliliters of 0.100 molar NaOH that you're titrating. So think about what that means in terms of millimoles. What is going down, what is going up, and use your equation here. With weak base over weak acid, right? Use that equation to solve this part. The second part, halfway point, that's not our equivalence point, but the half equivalence point, right? What we just talked about on our graphs, pH is equal to the pKa there. So that's something I know you're able to solve. And then the equivalence point, we're going to have to come to this one together in a second. Go ahead and do A and B. So A, what is my pH after 8 milliliters of 0.1 molar NaOH has been added? Okay, hopefully you were able to figure that out. Go ahead and do B. That should have been even easier. Just plug in your Ka value, negative log of your Ka. All right, here we go. So I know that at my equivalence point, I've used 50 milliliters of NaOH because these are the same concentration. So I have to keep that in mind. So if I've only added 8 milliliters, I am definitely nowhere near that equivalence point. So I'm still going to be basic. My pH here, I have to use my weak acid and weak base. I know I'm starting with 5 millimoles because I have 50 milliliters of 0.1. All right, 50 times 0.1 is 5, so 5 millimoles. And I know I have no weak base to start, so that is 0. And I'm going to end up making 0.8 millimoles because 8 times 0.1 is 0.8. So minus 0.8 on the top, plus 0.8 on the bottom. And I multiply that times my Ka, I end up getting a value of 3.255 times 10 to the negative 9th. Negative log of that is 8.49. I can go through and do the same thing at the halfway point, negative log of my Ka value, and I get 9.21. All right, for the equivalence point, this one I'm just gonna throw up the answer and we'll walk through this together because this one's a little more challenging. Okay. All right. So here we are. At the equivalence point, I know that the moles of acid equals the moles of base, and that is equal to the moles of salt formed. I know because I'm at the equivalence point, I have 50 milliliters of my hydrogen cyanide gas, and I have 50 milliliters of my NaOH for a total volume of 100 milliliters. If everything's equal, my 5 millimoles of hydrogen cyanide gas has been neutralized, so that's equal also to the moles of base, and that's equal to the moles of salt formed. I have to look at this as a salt problem. I have to look at what my weak acid and strong base will form, which turns into a salt of sodium cyanide. Now, if I look at where those things come from, strong base and weak acid, well, the strong base always wins. So this is going to be a basic solution. So when I look at the Rice table for this, I have to set it up as the cyanide ion of my weak acid being mixed with water to produce OH minus, because I know that's what's going to be in excess. So set up my Rice table that way. I have 5 millimole over 100 milliliters. That gives me 0.05 as my initial concentration. Minus x plus x plus x, the works. Now here, also because I'm forming OH minus, since I form OH minus, I have to use a Kb value here, and I'm given a Ka. So I have to solve for my Kb, and when I do, I get a Kb of 1.6 times 10 to the negative fifth. I can neglect my x here, and when I do, I get an x of 8.98 times 10 to the negative fourth. And of course, we have to be careful because that's our OH concentration. So then that gives us a pOH of 3.05. I end up with a pH of 10.95 at the equivalence point. This makes sense if we were thinking about our graph, right? If our graph is here, and this is 7, I've got a weak acid, and then boom, strong base, right? So I've got this very long buffer region, and then up here in that region of 10 to 11 is where I hit my equivalence point because I'm titrating with a strong base. So think back to the graph. Does the answer make sense? Certainly does. Okay. We also need to look at indicators and when is an appropriate time to use one. With indicators, we want to use an indicator that is within the range of, like I said, pKa plus or minus 1. Since its useful range is pKa plus or minus 1, that can tell us what region we're looking for. So here it says we're titrating ammonia, which is a weak base, with a strong acid. Okay, so ammonia's Kb value, you'd have to look it up, but it's 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth. If you think about the negative log of that, which would be our pKa, that means we're looking at a range of 5 to 7-ish for our pH, right? We want our indicator to be in the range of pK plus or minus 1. So negative log of 1.8 e to the negative 5. So that's like 4.7, about 5, right? 5 to 7-ish. All right. So if we look at the methyl red region here, we can see that our equivalence point right there, methyl red certainly falls within that range. If we look at methyl red, it's got that changeover point right here, that transition point in that 5 to 6 region, which is right in our zone. We want the color to change when we are very close to our equivalence point. So the color would start changing here at about 4.1 or 4.2, and we hit our equivalence point shortly at the end of that. Okay. Okay, that is all for today.